I wanted to use the idea of a simple inclined plane as a means of attempting to move us towards something that has to do with rotational motion and how it is different, also how it is similar to what we've already discussed. We got bogged down with the details of a problem from first semester that prevented us from making real progress. So let's start with something similar, but I want to do so from a slightly different kind of direction. Maybe if I don't rely as much on some of the more, I hasten to use the word complex. If I don't rely on some of the prior knowledge from last semester and maybe make this more fresh, we'll have more success. But the whole point of the way this physics instruction is based is on building on what you've already known and adding small incremental changes each time. So we're not going to get away from net force equals ma, net force equals 0. I mean, we are teaching Newtonian mechanics. Newton's rules are likely to come up. Fair enough? So yesterday I gave you the conditions that are required for an object to roll. Do you remember that? In that discussion, or as part of my discussion, I tried to give you some things you could count on. And one of them was that for an object to be considered rolling, there has to be a single point in contact with your surface that is instantaneously at rest with respect to the surface. I said it like 4 or 5 times to make sure you would write it down. And it should be there in the old notes somewhere, right? Now that's part of the conditions for rolling, but it's not all of them. Although that has to be true, that's also true for an object at rest, that a point is in contact and is not moving with respect to the surface. It's also true for a block sitting there. I mean, all of those things are true. But to be rolling, there's something else. And this is a condition for rolling. And I don't know if you understand why saying the word condition instead of rule is important. But the condition for rolling involves these 3 things. And what I believe I said yesterday was that if I tell you something is rolling, these things have to be true. But if I ask you if something's rolling, you might have to prove them to be true. But those are 2 different things. That's why this is a condition. If something is rolling, these things, these ratios, will have to be true. So you could prove to me something is rolling by showing me that an object's linear velocity and angular velocity are equal by an order of the radius. Right, that's what this says. And I picked velocity on purpose because I'm going to use it here in a minute, but I could have picked any one of these 3 things. You could show me that the full displacement of the object is proportional to the angular displacement of the object, right? These are things that are related, but they're still related by the radius. That's what this condition is. So I'll tuck this away for a minute. I want to come back to it, I'm sure, but I want you to consider a different situation. Imagine a situation in which I have a section of an area that is very smooth and another section of the area that is rougher. And I have an object, rounded object, that currently has a velocity v0, but has no angular velocity at this moment. So it's going to approach an area that has friction. Now, can you in your head imagine that when this object hits this place, it's going to transition from sliding to rolling? Does that make sense? So there's going to be a period in here when the object will hit this area and will experience a frictional force. Now, before it does, I think we probably can note that here the net force would be 0. As it slides, it's got forces acting on it, but they're all balanced, which is why it's velocity isn't changing, right? It's got an acceleration of 0. There's things acting on it, weight downwards, normal force upwards, but there's no lateral forces, so there's nothing to change the object's velocity. But the moment it hits this area that's rough, we'll suddenly have a force acting in this direction at the point of contact. Now suddenly, the object is experiencing an unbalanced force, and therefore it's going to accelerate. I'd argue that after a few moments in this region, its velocity will become a smaller amount. Right? That has to be true. Newton's second law states that if there's an unbalanced force acting on an object, it's going to accelerate. And based on the information presented in this problem, the acceleration is going to be to the left. Since the object is moving to the right, this acceleration will seek to reduce the size of the velocity. All reasonable ideas? Now, I also recognize that this force is acting at the edge of the object. Now, there are two other forces acting on the object as well. There's the weight, which is acting downwards, and there's the normal force that's acting upwards. And if I was to consider drawing those, just to provide a point of information, the weight acts at the center, and the normal force acts from the surface and goes through the center. Does that make sense to all of you? Any question about those choices there? All right. Those forces still exist when we hit the patch where there's the friction. But I believe that frictional force, because it acts at the edge, is going to cause the object to begin to rotate. Isn't that going to have to be true? Because not only do I see an unbalanced force, but that force is acting apart from the center of mass. If there's a pivot point at the center of mass, then this is probably going to cause a torque on the object. And that torque is going to increase the object's angular speed, because the unbalanced torque will cause an unbalanced acceleration. Not unbalanced, it will cause an acceleration, but an angular acceleration. And I think that this frictional torque is going to be to increase the object's angular speed. So I think this frictional force does two things. I think it decreases the linear velocity and increases the angular velocity. I think it plausible that if we wait long enough, we should reach a point where the linear velocity has reduced enough and the angular velocity has increased enough for a condition to be met. Do you understand where I'm going? Let me not have any hyperbole here. I think we might reach a point where this condition is met. Right? The velocity is becoming a smaller and smaller number. The angular acceleration is becoming a bigger and bigger number. They may meet. And when they meet, we are no longer slipping, but we are now rolling. Let's consider just the things we know. For example, this period where the object hits the area with friction. When I first start that area, I believe the net force will be equal to ma. Right? I have an unbalanced force in this region. So we go from a first law problem to instantaneously having a second law problem the moment we get here. That makes sense? I'm going to call this our zero. This is where our problem begins. I think there's only one force acting, and I think it's friction. But if I recall, friction is equal to mu times the normal force. And since we're on level surface, the normal force has to be equal to mg. So I think this will be mu mg. Any question? Now, judging from my picture, the initial velocity is to the right, but this frictional force is to the left. For consistency's sake, I'm going to make to the right positive. And that would suggest then that minus friction equals ma. if I was to look at Newton's second law. Right? And if I do a substitution, I'll get minus mu mg equals ma. Good enough so far? Now, I'm going to notice right away that I can write this as A equals minus mu g. Let's stop here for just a minute. Let's forget that we're dealing with this ball. Let's forget that we're dealing with this rough surface. Mu is a constant, g is a constant. This represents a constant acceleration, doesn't it? That unlocks, in my brain, a whole bunch of things. Don't have to do any calculus here. I've done the calculus on this, right? 2 things, maybe more, maybe 5 things. It's supposed to have been memorized long ago. In fact, I think, just looking at this right now, we could probably come up with a reasonable relationship for how the object's velocity is going to change. Right? Now, if I had said from the beginning of this, here's a ball sliding towards a region of space with a coefficient of friction of mu, derive an equation for the object's velocity as a function of time. Do you think you could have done it? Did I do anything here that we haven't done? So you understand the disconnect, right? Nothing new, all first semester stuff. So maybe, since we are 13 minutes in right now, I'll hit the old pause. Let's get back to this. Everything we've done to this point is old news. However, what we're about to do now is new. But I will, not new in the sense that I haven't taught you this. I've taught you everything we're about to do here. New in that we're going to apply it to this question. Because I believe the frictional force is causing an unbalanced torque. So, Newton's second law for torque states that the net torque will be equal to I alpha. Now, I don't know what shape this object is, and I purposely don't want to choose a shape, so I'm just going to leave the I there for now. I have nothing to substitute in, and I'm not going to consider subbing in. I think I'll sub it at the end. Is that okay with all of you guys? There are 3 forces that act on this object, but I believe the most reasonable place to make our pivot point to be the center of the object, especially when it first hits the region of space where there's a frictional force, because I believe at that instant, the only force that can be applying a torque is friction, and it's going to, at that instant, experience an acceleration about its center. So I think this is a reasonable thing to do, is indicate that the frictional force is causing a torque. The normal force can't cause a torque in this instance, because if you look, the normal force is directed towards the center. So the angle of that force prohibits it causing a torque. And similarly, if our pivot point is at the weight, then the weight can't cause a torque either, because that's where we place our pivot point, right? So the torque arm length would be 0. So the frictional force is the only one that's in the correct direction and is located at a place where it could apply a torque for it to count. So I'm going to remind myself that torque is R times F times the sine of an angle. And I'm going to look at where that force is applied and recognize that the size of this torque is capital R, the radius of my round thing, times the frictional force, which we already have derived. It's mu mg times the sine of 90 degrees. I think we can pretty well see that the radius would strike the ground, but friction has to be perpendicular to the radius. So we all good with that? That has to be equal to I alpha. Any questions? Yeah.
So could you do this problem by choosing the pivot point at the edge of the ball, or no? Since you said.
No. You can't.
So what was it with the ribbon that with the two different pivot points?
It was because the ribbon was oriented to the side, and part of it was that if you looked at it, yes, that point on the side was not moving with respect to the disc, but there's a clear torque because of the angle of the weight acting on the center of mass. This one, the moment it instantaneously strikes the region with our coefficient, that instantaneous moment, the frictional force is applying a torque to the center of mass. Now, if we wanted to place the edge as our pivot point, we could, but we would have to be in the inertial reference frame of the ball to do so, which means the ground is moving and the ball's in place. Does that make sense? If we do it that way, then we would be able to use the inertia of the ball as our means of calculating the torque of the point that's in contact with the ground. But I think for all intents and purposes, it's easier to look at it from this standpoint than to look at it from that standpoint. Also, this allows me to use a moment of inertia that doesn't involve the parallel axis theorem, and I think that's easier for this instruction, okay? Now, I do want to reduce this a little bit by getting rid of the sine of 90 and just expressing it as I alpha. Now, I want to make a similar argument here. If I solve this for alpha, I'll get R mu mg over I. All of those things look like they're constant, right? The surface isn't changing, the size of the object isn't changing, its shape isn't changing, its mass isn't changing. They all look to be the same. So I think we can say again that the acceleration is a constant. That unlocks something for me, doesn't it? Suddenly I know that omega equals alpha times t plus omega naught, and delta theta equals 1/2 alpha t squared plus omega naught times t, and so on and so forth, right? Doesn't seem like it'd be too much work for us to come up with a relationship for the angular speed as a function of time. Right? Do you see that okay? So I'm going to do so. Omega equals R mu mg over I times t plus 0, because the angular speed is 0 at time 0. Make sure. Now, do you see that this is the same thing we just did? But again, from the very beginning, would you have been able to derive an expression for the angular speed as a function of time? Because that's what we've done. But now we've done it twice, right? I've just tried to reinforce the same thing we've done quite literally 5 minutes ago. We've done it twice now. Now, the reason we were able to do it this way is because the acceleration was a constant. If the acceleration wasn't a constant, we might have had to use a differential equation to do so, do some integration. Take the acceleration, set it equal to d omega dt, and then do some integration. That would work, and we've talked about that. Don't be scared when they say derive something. You know where velocity exists in physics now. So when you're asked to find velocity as a function of time, don't look at energy. Time never shows up in energy, but time does show up as a derivative, and it does show up in motion equations, and it does show up in impulse. These are places you could go to get something as a function of time. Don't be scared off, just look at the places where we have time as a feature of our problem. But I want to come back to all of this. From the very beginning, the whole point of this was to discover when does this object, or where does this object start rolling? We're looking at the transitional time. If we look at what we've developed, I'll get them both in there, I have velocity, and it's becoming a smaller number, right? I'm starting here, and I'm taking stuff away as time progresses. On the other side of that, this is the angular velocity. It starts at 0, and it becomes a bigger number. As time progresses, that whole term gets bigger. The conditions for rolling are clear. Oops. These are the conditions for rolling. When this equals this times the radius, we're rolling. And I use that word correctly, when. We have an expression for how fast the object is going with respect to time. We have an expression for the angular speed with respect to time. When are these equal? When they are equal, we're rolling. We're no longer sliding. Now you could solve this for t. That's what I'm asking you to do. When does the object stop slipping and is now rolling? I'm going to do a little reorganization, but do you see what we did here? I didn't teach you anything new except this. This is the only thing we did. The only thing I did is show you how to use the condition for rolling. That's the only new thing today. I said we want to know if the object's rolling. I'm saying I could tell you when it's rolling. Now, I could have used different motion equations. You understand? I could have used motion equations that talked about where it is. I could have put delta x in them and used a different one. It didn't have t in it. We could have found out where the object is when it's rolling. But I think that one's harder to use because I don't think the outer edge of the thing that's spinning will move the same distance as how far it slides. So I don't know if that one would have worked. But I do know that the time it takes to get to this point will have to be the same for both. Right? It has to be. We just showed that this has to be true. And there is clearly a t where this happens. Let's find it. I'm going to rewrite this a little bit. Not much, but I'm going to take this and move it to the other side. That seems to make sense because it's got t in it. And I'm going to reorganize what I have here because I want to put the mu and a g together, and I'm going to take that r and combine it with the other r. In fact, I think I could write this one other way, and bear with me when I do this. In fact, we wanted a time, so if you don't mind, I'm going to keep going if that's all right. You guys good with that? So solve this for t. Maybe one more step because you guys in your algebra is often cloudy and inconsistent. Not all of you. But I like writing out steps, and my brain puts together patterns. And I hope you see some patterns here. So now I will solve for t. There. Think we did okay? You guys good with that? I think there's some stuff here. When does this happen? Well, it looks like it will take longer for that to happen if the thing is thrown faster. That makes sense too. Also looks like if the surface is stickier, it'll probably start rolling sooner, right? that number gets bigger, then t becomes smaller. Makes sense? I left this like this. Do you see why? I is going to be something with mr squared in it, right? Mr squared is going to cancel out. This is going to be something that I add to the number 1. So I'm pretty sure all of this, regardless of what the shape is very likely to be less than 1. Right? If it's a disk, I'm going to have a 1/2 in that parenthesis. Right? If it's a solid sphere, I'll have 2/5. If it's just a hoop, I'll have just 1. But that whole thing is going to be less than 1. Something's going to scale this less. In fact, we can kind of figure out what will take longer or shorter to get spinning by what I does to this particular relationship, right? All right, go away.